Hello. Welcome to all my combo lords joining me here in the combo classroom today. Another nice sunny day with the birds, although it's a little shady back here, but we get our sun rays at moments, for better or for worse. Kind of hard to dodge them during some filming. But it's nice to have you all here. Thanks for all the early commenters for leaving your thoughts. And today we're going to be doing a little stream related to mostly some fun mathematical, what I was calling programs that were on my computer, or that I just downloaded onto my new computer this morning. I don't know if I'm using the right terminology when I call them different programs. They're little mathematical interfaces or visual interactive demonstration things that will show us ways of visualizing some of the number theory concepts we've been talking about, like where prime numbers live, what numbers would look like in different bases, and what factors make up numbers visually and algebraically. And by visually factors, we could imagine numbers like rectangles and such, or even as grid points in one of these. So I basically only flipped through a few small handful of certain programs out of this place called the Wolfram demonstrations page. Wolfram is a company or whatever that makes a really good online a really good online calculator in general, which that is my go-to usually to pull up what's called Wolfram Alpha. And if I need to do some quick calculation, they're actually pairing up with ChatGPT, that robot that I have mocked in the past, soon, which will save ChatGPT probably from its terrible math skills, because not even just in terms of mathematical accuracy, which the online calculator is not perfect on Wolfram Alpha, but they're pretty good unless you throw wacky stuff at them. But also even just in terms of logic. They might help that ChatGPT be a little less contradictory. Now, apart from having a good calculator and even a good Wikipedia-like section where you can go to what's called Wolfram Math World, and they have pages about many topics, sort of like a slightly less long but slightly more trustworthy in terms of how they phrase things version of what Wikipedia might have for certain math topics. So if you're interested in a random topic in, say, number theory, not only is it good to look through the Wikipedia page, but check out if they have something on Wolfram Math World. And then there's a whole nother thing, which would allow me to edit the programs I'm about to show, as well as would allow me to have a bunch of their online stuff and more just on my desktop. It's called their Mathematica program, but that costs money. I'll see if I get that later. What they had for free, because they do have a lot of cool free resources, is all of these different demonstrations where you just download a thing called the Wolfram Player or the Wolfram Notebooks Player or something. And I did that because if I want to take up a few gigabytes of room for some program on my computer, that seems like one of the best options. And of course, for those who didn't see the last stream, this is on a new computer. As a quick synopsis of what happened, as I was trying to show the properties of the Toro Flux to a family member, and my old computer was there, they leaned over and knocked over a cup of coffee they had put down all over the computer and broke it, and helped me get a new one. So this one is probably even improved in some ways. So we have a new and improved computer, although due to an accident. And on this computer, we're going to pull open this new thing that I downloaded, which, like I said, I called them programs, but they technically are all just different sub-coded things all played through the same program right now. But maybe you could call them different programs because I'm sure they have different codes for each of them. I'm not a programmer, I don't know. If you are a programmer, reach out to me. And to those who have reached out to me, I may be a little delayed, but I'm going to catch up on getting back to some emails to some people who have reached out because a lot of my schedule got delayed by this computer shift, but we're mostly back on track. Now, it did delay the last episode on the main combo class channel, but I got that out Monday night. So make sure that after this stream, if you haven't already, watch my new main episode that is a more condensed 14-minute mathematical thing about modular division, which is linked in the description. Now, before I pull open our demonstrations, I will note that I'll answer this comment real quick that asks for a suggestion for young math enthusiasts. I would recommend reading a lot, and as you read, taking notes and trying to connect topics and doing your own little experiments with numbers, not rushing to look up an answer, but sometimes playing around with things and then checking how what you found lines up with things that may already be known or not. And so I would recommend reading and note-taking over most things, but, looking at these interactive demonstrations is another way that you could train your brain, because these are going to be a way of visualizing certain things that you can't necessarily put in a book. We can visualize them better when we have control over clicking through them, and I can give my commentary at whatever speed I want and then click to the next thing. So I like to think that watching my videos and trying out resources like this yourself are also helpful. Someone asked for a riddle. Send plus more equals money. I'm not sure if you mean just a joke or if you mean that's some substitution cipher where each letter stands for something. If it is a substitution cipher, maybe you could figure out what the letters have to be, if they have to be integers or something. Or maybe it's just a joke. To anyone who does want to help monetarily with the combo class, though, there is a Patreon. So that's in the description as well. And a Discord where a lot of people chat. So to start off, though, before we rush into all these demonstrations, which I'm sure will very much distract and sidetrack me with many facts I want to share, I will note a few things about what's upcoming in combo class. We are about to hit a new month of May. Be warned, like I said, the first day of each month in combo class is that month's Fool's Day, sort of like April Fool's Day. And we're going to turn April Fool's Day into a whole Fool's Week for April. The rest of the months can have one day at the beginning. But, of course, if I ever do an April Fool's, I will say within a minute of it that it was an April Fool's. If you prank someone, it's good to clarify that it was a prank after. Of course, I'll have to prank some people with the Toro Flux somehow on April Fool's Day without causing any more computer problems. So what's coming up in combo class is I have a bunch of footage more filmed than edited due to having to shift computers, but what I do have filmed that will be edited shortly is a short for this channel, which I'm getting back to filming shorts in one of these days soon once I'm a little ahead on my main combo class channel and I have a camera person over and I'm already ahead on those episodes. I will film a bunch of shorts because I have them all written down. So we'll have those coming back. There's also 2 shorts I filmed more that I might put on the main combo class channel. In fact, at least one of them I will. And that's because the shorts did so good at attracting people to this channel that at first when I made the combo class channel, I only wanted the longer horizontal videos on there for sure, like only that. But that was partially because they amalgamated them worse and they had the shorts in the same videos tab, and it was harder to see the stream of main episodes in a row without having to go to a playlist. But now they kind of fixed that to a degree by having the live, or like different tabs for live and video and short. So since they did so unbelievably well at attracting people to this channel, and they still are, YouTube's still promoting their favorite of the shorts from here, I'm probably going to put my favorite third or quarter of the shorts I make on that channel instead. I'm going to make sure there'll be less of those than main episodes, because I know that channel is more for flowing like a TV show of main episodes. But for little facts that I make a really good short out of, in my opinion, going forward, they might go on that combo class channel. So even if you don't watch my main episodes, better make sure to be tuned in there as well. I also just want, at least for a few shorts I put out, more people on the shorts page just to see, oh, that weird lab coat math guy with the clocks, this is this other sort of main, in a way, channel of his, although that one has far less subscribers. It did just pass 27,000, which is a neat number because it's a perfect power, and I've been taking some notes about how it's interesting that like 27 and 25 are both considered perfect powers because they can be expressed as some positive integer to another positive integer's power, and with the power being at least 2, the one in the exponent. And so like a number 1 and up, that's a whole number, to the power 2 or up, that's a power, is one way of expressing it. So 25 can be expressed 5 squared, 27 can be expressed 3 cubed, and it's interesting that both of those are perfect powers, but 27,000 is a perfect power and 25,000 isn't. So try and think about why that's the case before I put that in an episode soon. It's a little logic puzzle. Which perfect power numbers are even amount of thousands and some number up to 3 digits in front of that with 3 zeros at the end, but are a perfect power? So you may get a clue from when we talked about prime signatures a while ago, which is just looking at the exponents of the prime factorization. So, somebody said, can I please say, what is my routine? Sure, but it changes a lot. So, this is not necessarily representative of my routine throughout life. I've had many routines at different times. Sometimes I've even had checklists that keep me on track and busy that I go through every day. But currently my routine is something like, I'll get up too early. I get up at like 6 or something, or 5 in the morning sometimes. Have some coffee and read and write notes about combo class or my books. And then most days film something with somebody or live stream. And then maybe see what some friends are up to in later on, particularly if it's a weekend. And hang out in my garden with my cats a lot. Read some stuff. Watch some YouTube videos. I don't have a very particular routine right now, but it's changed a lot. I went through 2 crazy surgeries last year. I'd get 2 hip surgeries, 1 in each hip. And so there's been a lot of routines even just in the past year or 2. So we shall see. Each grade might have its own routine. Now, I got sidetracked by the comments, but what I wanted to note was what's coming is, apart from a few shorts, I also have a bonus video about finding more slender salamanders around here. That'll be coming out on this channel. I also have the next main episode that's coming out on the Combo Class channel is sort of a snack break episode, but it's probably the most mathematical of the snack break-like episodes. It relates to bananas, which is why I have this extra small one here. And I have a bunch of them of all sorts of sizes inside that are going to be seen in the episode. But I only brought one out because there were some flies around here and I don't want to attract fruit flies or anything. And so we're going to look at a mathematical property I realized about bananas. And if anyone wants to think about this on your own in advance, think about, what mathematical similarity do bananas have with wasp nests or beehives? I'm saying both because, whoa, did a spider just come out of that? Whoa. Spider might have moved into that and dropped out. But I need to watch back on that live stream. A spider fell from somewhere. It might have been out of this when I picked it up. So, I hope there's not any more in there. So, if you want to think about it on your own, don't leave a comment, because most people probably won't guess it. Something weird I realized one day, just like a few days ago, and I was like, I'm not quite ready to film all these other math episodes that I have ready for the Combo Class channel, brainstormed. This week I might need to do a snack breaky episode, but it will involve a lot of math. It's, involves bananas, beehives, and math. So that'll be fun, coming out this weekend. And the other thing I mentioned in this stream, apart from our interfaces, are keep an eye out for squirrels or birds, because there's a lot of bird seed that got spilled on the ground. The squirrels knocked a lot out of the feeder, although this time they left a little in there. They didn't completely knock the bottom thing off. But there's a lot of bird seed on the ground that they've knocked over, and I knocked over some by accident. But that's been attracting a lot of them. So now if I enter the combo classroom very quietly, sometimes there's a squirrel or bird hanging out here, and they don't leave until I get pretty close. So what I might have to do in a minute is go grab the bag of bird seed at some point when we're taking a break from the demonstrations, and come back really quietly and see if a squirrel comes in the meantime, because it's a lot more common since I spilled that bird seed. I also want to grab them a few more pieces of the type of nuts they like. I read that they really like unsalted walnuts or pecans, and I put some out for them that are gone, so presumably they ate them. Now, finally, our last thing we'll note before I pull open these math demonstrations is, look at this thing growing out of the potato. We'll get a closer look on my camera sometime, but do you see this potato plant growing? Now, nobody's allowed to eat it. Even the greens, I think, are semi-poisonous, and if we manage to grow fruits from it, which are a berry technically, but, you know, a banana's also botanically a berry. So, if we grow those berries, they're really poisonous, so we're not going to eat them. The goal is to get to the stage where we can maybe hopefully grow a fruit just to document it, and then we'll remove it all. So now it's time to pull open some math demonstrations. And to anyone who leaves more comments, note that I will check them every 10 or 15 minutes. So feel free to leave any questions. I'll probably get to them at some point, but not immediately. So let me shrink myself a little bit. And back here, we got some blank space where the first thing I'm going to pull up is one we've seen before. I've shown this one on the online version, which I'm worried it makes it way harder on the computer. So this is the downloaded version. I mean, harder to stream at the same time as doing it. So here we got the downloaded version of fractions in different bases. Now, this was a really neat table that now we have quicker access to, and we can change its size easier and stuff like that. Shout out to whoever made this. So it was contributed by Stephen Wolfram himself, the guy who founded Wolfram. So this shows us, as an example of what demonstrations can do, what fractions look like in different bases. Now here, I'll shrink it a little bit back again. Hopefully it's visible at this size so we can have it next to me. And for example, if I want to say, how do fractions turn to decimals in base 10? Well, tenths, this is interesting. They're showing the, no, we're in base 5, that's why. There, that makes more sense. So, tenths in base 10 look very predictable. What about ninths? Hey, look, 0.1 repeating is 1/9. 0.2 repeating is 2/9. Hey, 0.8 repeating is 8/9. And you know what? Does that mean 0.9 repeating is 9/9? Yes, it does. These different last digits at the end are just because they did round at the end, but would have been 6s forever there, 7s forever there, and etc. Now, what about, for example, if we're in base, well, in base 10, let's just note that good fraction. Not great, but workable. 1 digit repeating forever. Decent. Good. Kind of alright. Some have a digit, then a repeating thing. Getting more confusing. Really wacky and weird. all these repeating strings of some permutation of 1, 4, 2, 8, 5, 7. Those are a little neater again, and those have that thing. What about base 6? Now we're in base 6. Good. Good. Pretty good. Workable. Good. Medium good. Not too bad. Pretty good. Not that bad. And overall, the base 6 fractions to decimals are way better. There was nothing on the way to 10 that gave me something as wacky as sevenths. Even sevenths in base 6 are a lot simpler. They're each a 2-digit thing repeating. We can also note the 2-digit thing repeating adds to 5 in each case. So, a lot of cool patterns in bases. And another one we could note is that for any base, the one right under it as a denominator will do those repeating strings. So if we counted in base 6, the argument wouldn't be does 0.9 repeating equal 1? The argument would be does 0.5 repeating equal 1? Because in base 6 it does. So, as someone noted, the repeating string in brackets, they noted that form in the comments. 1/7 has a 6-digit repeating string, whereas in base 10, but a 2-digit repeating string in base 6. Way neater. And you'd think, oh, but base 10 is good at handling fifths. So that must be really helpful. But not only is base 10 bad at handling thirds, and thirds are a bit more fundamental than fifths, whereas base 6 is great at handling thirds, base 6 is actually not that bad at handling fifths. Fifths do the repeating thing that ninths did in our base. So it's like, even the one case that base 10 is normally better, it's kind of neat here too, and easy to remember. So, someone's asking, how did someone code the first coding language when there weren't any coding languages to begin with? Well, you'd have to start from scratch, where computers are almost like chains of little reactions of items being flipped on or off, representing binary states. And you make a little chain reaction of things flipping on or off, and first you get through the state of that simulating a calculator, and then you get further. So I don't know a huge amount about it, but as I learn about it, you know, maybe some episodes will come out of that process. It's interesting. And the next time computers show up in an episode will be either an episode I will do at some point about my opinions about AI and my collection of the dumbest answers I've gotten from the ChatGPT math thing, mixed with all the headlines and claims that it was good at math during that time. So I know it's better at math now, but it does tell you something about not believing whatever they're saying it's good about, because they were saying it was good at math when it really wasn't. And so, and it was saying, until you probed it deeper, and then it said, it admitted it was just good at pretending to be good at math. So that'll be an episode at some point. And there will also be one that will be in the near future about a base that some computers use instead of binary, called balanced ternary, using the digits 0, 1, and a digit that represents -1. So, those are the comments for now, and this was already an interface that not only have we already played around with once or twice, but additionally, we will see these patterns in other forms in an episode. I'll show more clear versions of certain patterns, like how we could say that 1 divided by b minus 1 has this pattern in a base. So we'll look at a few patterns that go in the future, like we'll probably have one like that that's sort of a flipped version of one of the first combo class episodes I made that was about divisibility properties 9 has, and how that secretly divisibility properties the number 1 less than the base you count in has. We might look at things like ninths and elevenths in a future one, sort of reciprocals turning to decimals of those. And how those represent b minus 1 and b plus 1. So, I'm actually surprised that when we learn so much about math that teachers don't make it as clear the patterns that the b minus 1 and b plus 1 number have compared to how much it gets drilled into your head the powers of the base number has. This is what powers of 10 do. This is what adding a 0 in our system does. This is what sliding the decimal in our system does. So we got to mix in a little bit of understanding 9 and 11, and similar to base 10 just being because it's the base number, those are the b minus 1 and b plus 1. Now, there's even, from that one of the first Convo class episodes, there's a number 9 spray painted on the side of my house, sort of like how I've now spray painted combo class here. But since 9 is mostly just a representative of b minus 1, I'm going to pretend that that 9 on the side of the house is actually an upside down 6, because you know we like the number 6 here in combo class. It's most underrated number, maybe. So, also one thing I'll note, just because I got to give 9 some credit, apart from being b minus 1 in our base, 9 is cool because it's, for one, and these are things that I was just trying to think the other day of cool properties each number had, and I didn't want to allow 9 to have the b minus 1 be its stuff. I didn't want base dependent properties. But I realized that 9 is, for one that is more commonly discussed would be that 9 is the first non-trivial, if you call 1 squared equals 1 being trivial, the first non-trivial odd square number. And odd square numbers and even square numbers have some different traits from each other. So that's a little notable that it's our first representative, apart from the number 1 itself, of an odd square number. But what I realized is that it's also the first odd number that's composite, because 1 is considered a unit, neither prime or composite. 3, 5, and 7 are all primes. So 9 should get some credit for being the first odd composite number. Now, let's pull open another demonstration. So, another one that we have here that we might as well do our other base-related one while we're at that. Or actually there's two more base-related ones. Here's just numbers in different bases. I think this one was also contributed to by Wolfram himself. So the semi-annoying thing I noticed about this is at first it lets you flip through all of the numbers. Why is it cutting the top ones off? No matter how I scale it, it's like I gotta scroll, I guess. Maybe I can shrink it this way. Okay, whatever. I gotta scroll to see those up there. But this shows the numbers, and the only annoying thing is it lets me do any of the small numbers, and we can see the highlighted one as base 10, so that's like your reference point. That's the number as we know it. But then they start skipping which number they allow, because they wanted to include some really big numbers as examples. So there's some point in the upper 2-digit numbers where they seem to stop letting you do them all. I couldn't figure out how to get in between. In any case, the low ones, we get all the numbers, which is neat. 1 looks like 1 in all the basic bases. Remember when I say basic base, that's because we've discussed a lot of cool wacky bases and will continue to. And so some people think these are the only bases, a number 2 or higher being an integer for the base. But I'm going to call that a basic base, the ones that follow all the properties you assume of a base, that its powers of an integer 2 or greater, and your digits range from 0 to b minus 1 for the symbols you use. But, and even more stuff you'd have to clarify, like where the powers of the numbers start, what you do with a point, like a decimal point and stuff. So You have to clarify a lot of stuff to really note that this is the type of base that people are referring to. So I'm calling that a basic base. Out of those, 1 always looks like 1. 2 mostly always looks like 2. We're getting cut off binary there. This is annoying. Why is binary getting cut off? So, in any case, we know binary represents 2 as 1, 0. So, now going up, we can see some patterns of different stuff. And this one's kind of neat, but we have an even cooler version that I'm going to add to the mix, which is a little calculator for different bases. So, first let's just see what some tables look like. What does an addition table in our base look like? We're going from 0 through 9 because to a degree the patterns repeat after that. Obviously the numbers get bigger, but to a degree we'll notice these patterns lingering and having traits in the next batch of numbers that end in these digits. So, in fact, if I cut off the first digit of all these and just left the last digit, this would be my mod 10 addition table. Same with here. If I cut off the first digit of any 2-digit one, if I only left the ones place digit, this is a mod 10 multiplication table. Here it gives me even a little more data because it's a base 10 multiplication table. So it also tells me how many of the 10s I got in addition to the remainder. So let's see how this looks. This is the thing we have to memorize when you're in school. Zeros, that's easy to remember. Ones, that's easy. Then you start getting here and they start getting hard to remember. It's, you know, once in a while, if I'm thinking really quick, I still got to remind myself which one's 56 and which one's 54. Some of these get annoying, especially when you get to like 11 and 12. I remember when I was in school, they made me memorize from 1 through 12, by 1 through 12. I don't think 0 was included. And it gets kind of annoying to remember things like 12 times 7. Now, I think it's a good skill to be able to, in your head, do something like 12 times 15 or something within 20 seconds in your head. I think that's a good skill. But just having it memorized, taking up a room in there, why? How often do I need to do that? So, some things it's good to just like be willing to spend 10 seconds calculating instead of having this massive table memorized in your head. In fact, it might be better. Maybe the calculating gives you practice at something. So, this is kind of annoying, but what if we were in base 6? Now, it shows a smaller section. So to be fair, let's pretend that we were just looking at this sector. Still here, it gets arguably a little confusing at first. You know, when you're first learning stuff like 4 times 6 is 24, 2 times 4 is the last 1-digit multiple of those. And there are things here that it's not as confusing yet, but it's still much more random than the base 6 patterns. Look at these. 0 makes our zeros, of course, and 1 makes themselves, of course. Now here, 2s have a very similar cycle that they had in ours. They're very comparable, where here they went 0, 2, 4, 6, 8, and then repeat it. Here we get kind of just a neater version of that. 0, 2, 4, 0, 2, 4 for our last digit. And we're adding 1 to the first digit here. Now, some things here would become really easy to remember, like how we can see that, well, I was also thinking more like fractions to decimals, like on that other table. 1/3 is 0.2 and 1/2 is 0.3. That's kind of like our base. 1/2 is 0.5, 1/5 is 0.2. But it's a little neater. There's less stuff in between. Our cycle goes 0, 2, 4, 0, 2, 4. And here our cycle goes 0, 3, 0, 3 for our last digit. And here it goes the backwards of the 2 one. 0, 4, 2, 0, 4, 2. Now, it's basically like if we had a 6-hour clock, and it's very easy to imagine going around thirds of it, or even to imagine how going around 2/3 of the clock worth at a time is the same as going 1/3 worth backwards. and then going half of the clock at a time. So we would remember that, like, the one that's a third of the reset is 2. The one that's half of the reset is 3. In fact, I just noticed 2 has a 3 cycle for its last digit, and 3 has a 2 cycle for its last digit. That's also cool. Now, 5 has them backwards, and in a way where they add up. Look, 0, 5, adds to 5, starting in 1, adds to 5, starting in 2, adds to 5, starting in 3, then 4. And that makes the last digit descend, the same way these ascended. So 5 has the properties that 9 has in our base. So basically, what do we have? 0's easy. 1's easy. These all have good patterns due to having a factor in common with the base. This is neat due to being 1 less than the base. It's all neat. And even 7, of course 6 is neat, that's the base. 7 is even neat because that's like how 11 works in our base. Then 8 shares a factor with the base, 9 shares a factor with the base, 10 shares a factor with the base. It's not until up at 11 that you start to get one that's harder to predict the patterns of. Whereas base 10, we're already acting weird at the 3s to a degree, and we're starting to act really weird at the 7s. So, base 6 is better. Base 12 also is the more commonly promoted alternative to base 10. Here, A represents whatever digit means 10. B is whatever digit means 11. But it's not as neat. This little sector, for example, that would represent the part that we had there, not quite as neat of patterns. So, part of the reason is because 12 is not as good at handling 5 and 7. 5 and 7 are neighbors with 6, but with 12, they're just these primes in its midst. Someone asked why I'm still outside. I like it out here. I have my desk out here. My room's pretty messy here. Okay, it's pretty messy here too, but I have room on this new desk for my computer to have space, and I got a bunch of math toys to visualize things. For example, I not only last time showed some of these puzzle cubes, and I was like, hey, you know, a lot of puzzles come in cubes. Well, here's the other one I was mentioning, that it does turn back to a cube, but it's really hard to. It's really hard to figure out how to morph this into its cubic state. So I got it once after fiddling around with it for a while. So I realized there's another cube. This is a popular one called the Soma cube that you try and put back together as a cube. And it involves a few polyomino-esque shapes. Often a polyomino, like a tetromino here, is just on the plane, but this includes some that weave through 3D. But they are still a form of relative to things like the tetromino, and my favorite, the pentomino. Do I have any of those around? Okay, here's a broken piece of one of the pentominoes, which makes it a 2-block omino, and you'd think, you don't know the word for that already, but you do. A duomino, a domino, a 2-cell thing, domino, is actually the same name root as the pentominoes that I love and the tetrominoes that people are more familiar with. So that's a little bit about how base 6 is pretty neat. Let's move on from the bases. We'll do a quick calculation or two, because here we had numbers, and I also had this, it was this one. The same one that had the tables. Also has a calculator. So, in our base, what if I wanted to know 7 times 13, like I said before? Okay, happens to be 91. That number looks kind of prime, but it's not. What if and there's not really that great of a divisibility trick to show that it's not divisible by one of these or is. What about base 6? That was a random example, but I think we'll be luckier because 7 is now written as 11, means 6 in this base. Wait, no, I want to be in base 6. Stop. Clear. So in base 6, 11 is how you write 7, times 13 would be written as we need 2 of the 6's plus 1. And this would be, I don't know off the top of my head the base 6 divisibility tricks, but I think that one we could do is that, yeah, here we go. Since this is the new 11, 7 became the new 11, we can do the 11 test. This works in other bases. We take the alternating digit sum of the numbers in like alternating spots, in this case adding 2 and 1, and then adding 3 separately. We take the difference between those, in this case 0, and we see if that's a multiple of 1, 1. And that divisibility rule carries over to this base, as we can see. It is a multiple of 1, 1 in this base, and it does do that. So, it would be a lot easier here in base 6. That's all of the 6 stuff for now, but 6 does relate to the mathematical stuff I realized about bananas that I'm going to put in an episode this weekend. So, now we are going to look at some non-base related stuff. So, an example of a non-base related one that I have is, before we get into a few related to primes, let's look at one that's about modular arithmetic. This is a really cool, colorful visualization of something that we've looked at before in terms of numbers, but here it's colored. So, what we have here is a little chart. Here, let's go to mod. Okay, 5's the lowest mod they allow. Let's start with mod 5. Mod 5, well, actually, let's do mod 7, because that's going to be like weekdays to a degree. So, here we can notice in mod 7, this is the plus chart, meaning it's an addition table. I'll explain restriction in a minute. And this is a key of sorts that tells us what they mean, so we can see their stripes better and how they behave in terms of clumping with each other. So, for example, we can see that this green stripe are all the values, as well as that green stripe, that become congruent to 2. Basically, when we add them up, their last digit in base 7 would be a 2. Or we could say, in terms of weekdays, if I went 6 days, then 3 days, it's the same weekday as going 2 weekdays. So if I'm adding this amount of weekdays to that amount of weekdays, then, this is my key of where I simplified land on. Because even though these numbers could add up to something like 12 weekdays is the same as 5. So, we can also notice that this is a weird visualization of how mod 7, as I showed in a recent-ish video on the combo class channel, that is linked in the description. It's the newest video there. Mod 7, being a prime mod, lets us divide by almost anything in that mod. By almost anything, I mean, sort of like how we can't divide by 0. In a prime mod, I can't divide by anything congruent to 0. So if someone asked me in mod 7, divide by 14, that's not going to work, because that would break down in that mod to being, we're trying to divide by 0. But for other values, we can. And That's because on the multiplication table, 0 turns everything to 0. So if I said I got a 0 and I want to backtrack where it came from, knowing one of the inputs but not the other, I can't. But if I said, hey, one of the inputs is a 3 and my output was light green, which meant 2, I know that the other one was also a 3. That's the only thing in the 3 row or column that goes there. Each of the non-zero rows and columns here touch each color once. Now that, combined with the fact that division is sort of like a reverse multiplication, and the fact that we wouldn't want to try and reverse and have multiple possibilities where it came from and say one was the answer, well, we can divide by any of these in a similar way that we could backtrack to a color. How about mod 10? Which ones touch every color? Well, there's 10 colors, so if they ever touch a duplicate color, they didn't touch all of them. For example, 2 goes in pattern. It's a 5-length cycle of what it does. So, with this, we can only see every color in the numbers that are co-prime to 10, also called relatively prime, meaning has no factors larger than 1 in common. So, for example, 1 technically fits that. It has no factors larger than 1 in common with 10. Touches every color. Same with if I went column instead of row. 2 doesn't. Has a factor in common. 3 does touch every color. 4 doesn't. Doesn't. Does. It's 1, 3, 7, and 9. Turn out to be, as we've seen, and make sure you've seen my episodes on the main combo class channel if any of the backstory-ish stuff doesn't make sense, because I don't assume people have seen all my streams, but sometimes what I'm saying builds off something I put in a full episode. So, 1, 3, 7, and 9, as I showed in one of those episodes, are also the digits that multi-digit primes can end in our base. Any prime number more than 10 can only end in a 1, 3, 7, or 9. We get an easier to follow rule in 6. Base or mod 6, primes can be in the spots 1 or 5. So, in terms of if you were a prime hunter and you wanted to know, I'm looking for primes and I want to have an easier time filtering out the spots they're definitely not, mod 6 would be great. However, if you were a modular divider and you're like, I need to divide a bunch of stuff modularly, I need to figure out where a bunch of clock times came from given how many times the clock moved but not how far it moved each time, or vice versa, given how far it moved but not how many times. That'd be equivalent. Which is neat, and something to note is that if we ever are using a clock analogy, there's sort of 2 clock analogies, because if I'm doing multiplication, I could say 7 minutes 13 times or 13 minutes 7 times. Same thing, because multiplication, A times B equals B times A, not only in the real numbers, but also in modular arithmetic. So, if you were a modular divider, you might like mod 7 better. So, someone's saying that the creator Jan Misali also made a video about base 6, and I need to watch that because I actually saw a website they made about base 6, which I agreed with most of. I didn't agree with all of the phrasings and stuff, but highly in support of the website that was advocating for base 6 and showing some reasons. Whoa, squirrel. Okay, we're going to do a very quiet section. Maybe that'll encourage the squirrel to return. This is going to be our ASMR-esque look at these graphs, so the squirrel might be less scared of my voice. In fact, here's what we'll do. I'm going to turn up the volume of the mic how much it's picking me up, so I can talk quieter and you can still hear me. And okay, in a little bit I'll go inside and get a pecan for the squirrel, and maybe that'll help lure it back. Okay, I'll probably go back to talking normal because I think it's not that far. I'll talk on the quieter end. So I need to see the video about base 6, though. I'll probably agree with a lot of it. Very interesting creator. I did like some of their videos I saw. So here we got our modular patterns. Now, it looks pretty beautiful as we sprout outward. Look at all these weird little patterns emerging. That is pretty beautiful. But there is also something we could do. Well, first let's look at these. Here's plus. Much more predictable. This is the addition tables. Now, what about times? That is much more interesting. But what about power? Now it's doing, let's see which one is the base and which one's the exponent. I'm guessing this axis is the base, but let's see. 2 to the power of 1 is 2. So yeah, this axis is the base, this axis is the exponent. So let's check that out. Looks like a weird creature. So powers are really cool, and we haven't done those yet, but we are going to need to bring powers into the mix before long. In fact, related to the follow-up I noted where I said, which things on the multiplication tables send a number to 1? Because that's another thing we can visualize here. Remember I said to those who saw that modular division episode at the end, we still have to unlock the reasons, more reasons or patterns behind why certain numbers pair up with another to create 1. So here with multiplication, we can see, well, in terms of multiplication, it's where are these white spots? But we can also ask other questions, like in terms of powers. We can see some white spots lurking. There, in 16, a lot of stuff goes crazy there. That's because we get a lot of these numbers, when they get to the right power, get congruent to 0. So, can you notice anything about the graphs that have black bars that aren't the one at the top? Which ones have a black bar that isn't the top? It's 8, 9, 12, 16. A lot of patterns going on. Now, there's also these restrictions up here which are interesting. Non-zero is a little boring. It means I don't want to see 0. I mean, it might help for now. We could just say they're the ones with the black was the question I was asking. But there's another thing here called units only. And the units, normally you're like, well, in math, the number 1's called the unit. And it's like, all right, there's a unit. What do you mean units? But there are extensions where we're going to use the word unit in other contexts, such as in modular arithmetic. Sometimes unit relates to which numbers have a modular multiplicative inverse, which is in that last episode on the Combo Class channel, what that means. But here we're seeing some things about units. And these make some pretty cool patterns. Look at all the spots where they exist. Now, what if I look at the times table? Prime mods have all that going on, but other divisible mods have all this stuff missing. 17, 16. 16 being a power of 2 has a really even looking grid of what's missing. 15, a little weirder. And we can tell what are we missing? Numbers that aren't co-prime to it. Numbers that share a factor larger than 1 with it. Which maybe here would be a good nickname for that. What if we call that, relatively prime is another nickname for what's often called co-prime also, meaning some numbers have no factor larger than 1 in common. Typically done with pairs of numbers compared to each other, but we could compare larger sets too. But what if we say ones that do have a factor in common larger than 1 are relatively composite? Even if one's a prime number, that's okay, because when you say relatively prime, one of them could be composite. So we could say relatively composite, referring to primes. So maybe that's a good new nickname. Relatively composite is what's missing here. Shares a factor larger than 1. Now, here, 14, we got some interesting gaps. 13 got everything because it's prime. 12 got a lot of gaps because it's highly divisible. 11 prime. 10. These are some interesting spots to note. So we'll fully explain why these ones are called units in the future. I know I haven't really gone into that portion of it yet, but we just did a lot of modular stuff, and we're going to I'll try and take a break from the modular stuff, even though I really love it. So I'm sure it'll keep popping up. But the next few episodes, maybe I'll make other types of math. Speaking of, another type of math that I love is prime numbers in general. Where do the prime numbers live? What are their patterns? For example, one of the first episodes I made on combo class was about, in my opinion, 3 questions that one might have if they were an ancient mathematician way back in the day. They might notice prime numbers were important, and that if we label these certain numbers primes, that every number has a singular unique prime factorization, at first just meaning every whole number, although we've shown how to extend it too. They might wonder, are there an infinite amount of primes? Are there an infinite amount of... Is it possible to have up to... you want to say infinite, but we're going to say arbitrarily large, to be technical. Can there be an arbitrarily large gap between the primes? Meaning, can they be like bigger than 1 million apart from each other with none in between? Can they be bigger than 1 trillion or any number you pick? And then, is there an infinite amount of times where they're really close too? So, like, is there an infinite amount of times that they happen, and that an infinite they happen far, an infinite they happen close? Well, the infinite question we can prove quite easily. Same with the arbitrarily large gaps. In that one episode, we showed both of those proofs, that there are an infinite amount of prime numbers, and that they get to have times on the number line where from one prime to the next number that's prime, it's bigger than any finite number you could pick. We want to feel like we could say infinity there, but technically we wouldn't say infinity and then there's another prime. We'll say there's no limit to how big the distance can be. So, what about closeness? Unsolved twin prime conjecture and other prime constellations and stuff. I'm going to do an episode before long about the other prime constellations. They're underrated. Everyone talks about twin primes. What about prime quadruplets? Those exist. So, all of those are known as prime constellations, which are patterns primes have in terms of their distance from others. And we'll have to make an episode about that to get the prime quadruplets and prime cousins and such. And a type that is technically called, I'm not the one who made this name, don't blame me, there's a type that is technically called sexy primes. And that's because it's using the word root sex for 6. They are primes that are 6 apart from each other. I'm not the one who named them, don't blame me. So we're going to have to talk about the sexy primes. YouTube, don't relate that to any demonetization stuff. And it's a math term. And the other ones, which are all types of prime constellation. We don't know yet for any of those types of prime constellation of the small ones if they do keep happening. However, it has been proven that there's an infinite amount of times that primes are within 246 or less apart from each other. Sounds random, but that's what the bound has gotten down to. You may see the numbers 6 or 12 that we've proven that, but there's like reliant on another thing that we think is true but isn't fully proven. Then if that was fully proven, we could get the bound down to 6 or 12 or so of infinite amount of times we know primes are that close. But to really solve the twin prime conjecture is the same question with 2 as the distance. And how about this question? Are there an infinite amount of times primes are 1 apart? Believe it or not, that's solved, and there's not an infinite amount of times. So let's see some comments. Someone's mentioning abstract algebra, which this modular arithmetic is heavily involved in, although we could also just call this on the number theory end of things. And abstract algebra is what we'll delve into as we look more at why do these patterns emerge, why do we build this system that contains these patterns, what's good about the systems, and when we look at things like that, some things to keep in mind are what elements do we allow in our set? Like here, we're just allowing these elements. Sometimes we allow all the positive integers. Sometimes we allow all the real numbers. What is in our set? How does 0 and 1 function and fit into that? Because those are usually pretty important. And which properties does the set have? One common one we might ask that did again come up in that modular division episode is the set closed under a given operation? Can we apply a given operation to members of it and be guaranteed to get another thing that's one of the members? In modular arithmetic, because it wraps around, it does work here where like any number to another power will, apart from this 0 to the 0 corner, any number to another power will be something we can express in one of these in this land. Now, a lot of people have commented on my things before. 0 to the 0th power is 1. Not really true. 0 to the 0th power doesn't work under the typical rules. In some fields, it is assigned the value of 1. But it's not 1 because the arithmetic works out nicely and spits out 1. It's 1 because in certain fields, assigning it the value of 1 makes certain functions or equations make more sense or be more well-behaved. It's inherently nonsensical because 0 to any power should be 0. Anything to the 0th power should be 1. So it's inherently going to cause a glitch. If I graph x to the 0 and 0 to the x, they don't touch. So it's going to break some rule or another, which is why often it's called indeterminate based on many things working as an answer to it. Sometimes you might see it called undefined, and sometimes it's assigned a value of either 0 or 1 to make a certain field work better. And 1 is more commonly used when that happens, but sometimes it's called 0. And in general, unless I clarify, I'm talking about this branch of combinatorics or whatever, we don't want to just say it's 1 because it's not 1 always or because of any normal rules. So, thank you to everyone commenting. I will show one more thing here, which is our sum of squares. That's kind of interesting. They show us if you add the square of each of these, what happens. And we get some kind of cool patterns there too. I like this plusy thing that keeps popping up there. That's pretty neat. If any animators want to work on making their own version of this, feel free to reach out to my email, which is on the contact link and maybe in the description here, I'm not sure. This one was contributed by Christopher Moretti. Shout out to that guy. So, what else do we got? This is some modular arithmetic, but we also got some other stuff. For example, we also got, well, this was my base calculator, but we also got some stuff about primes in general. And we're going to start, what's table of primes, which is this? Oh, this is sort of the same thing. This is sort of the other thing once we filtered everything. So this is our better version of this. This table of primes, we may have seen on a stream before. I forget if I've only played around with it on my own or if I showed it in a stream. I think I might have shown it once. but it's worth seeing because we're going to add some more details to our description. So, prime numbers can be hard to find. They have weird patterns. We don't know all of the details about how they clump on the number line. We know certain things. For example, don't worry about... Okay, so here's the number line so far, or the number square, where it happens to be like that amount of numbers by that amount of numbers. We can change those in a minute. But what's happened so far is they said, we're going to unhighlight the ones that aren't primes as we hunt through these. We're going to try and eliminate all the non-primes. This is a classic method. This guy who it's named after was from literally the BC era, more than 2,000 years ago. So this was one of the first and still classic methods of looking for primes, is one number at a time, apart from one, which just gets eliminated. All the following numbers, we will, for the first number that isn't eliminated, keep it, but eliminate every multiple of it. So we could think of that as from 2 was the first thing left after 1. We have eliminated not 2 itself, but anything 2 from there, 2 from there, 2 from there, 2 from there. Anything that goes 2 at a time. Now, the odds and evens look like a checkerboard here, but what if I change the width? Half of the widths, they look checkerboardy. Half of them, they look like lines. And that's because depending how long my array is, I sort of see modular or base-like patterns, where here it's like my array goes from 1 to 14. It's almost like I'm in base 15. And 0, 5, 6. I guess no, there's more like base 14, but we don't start from 0. It's a little different, but in general, with it being in these columns of 14, we can have divisibility by 2 for them to show out super popping out like. If I make it an odd number for my width, then it's going to look more checkerboardy. What about when I eliminate more? Well, after 2, when I go to 3, now also let's note, if you were doing this and you didn't want to have to look 2 ahead and look 2 ahead and look 2 ahead, it would be faster to make it a width that helped you eliminate entire columns, which also line up with last digits sometimes. Like if my thing looks kind of like base 10, where it's going 1 through 10, 11 through 20, and so on, there's 10 of them, 10 total columns. If it looks like that, then the last digits line up with what we expect. Here's the last digit 8 column. Those are all even. Here's the last digit 6 column. Those are all even. So it's easier to eliminate the ones that are a not co-prime with your mod number, that do have a factor in common. Especially here, 2 is a factor of it. What about 3? So if I now say, graph, keep 3, but eliminate every third one, which is going to be like, okay, 6 is already eliminated. Ooh, now we remove 9. 12 is already eliminated. Ooh, now we remove 15. There we go. And, yeah, we've removed the 3s as well. It looks a little confusing because the 3s hit in these weird diagonal ways. So maybe I would say, let's make it 6 or 12 across. Then we'll have patterns for 2s and 3s. And it's true, if I make it 6 across, wowie zowie, 2 and 3 are prime, and all of the other possibilities for primes, we haven't narrowed down that all these are prime, but we've narrowed down that none of the unhighlighted ones are in these neat lines. So it's like, okay, as long as we remember that 2 and 3 are prime, we know that all of the rest are in this first column or the second last column, which is sort of representative of, in mod 6, 1 and 5, and in base 6, numbers that end in those. Meaning in base 6, every prime is either the number 2 or 3, or ends in either a 1 or 5. So, what's next? We don't need to filter 4, because any multiple of 4 was a multiple of 2. So that's why it's going to tell the program, We just need to go to the next. I mean, okay, this program I'm sure was already programmed by the guy, whoever it was, George Beck, shout out to him, programming in the list of primes we'd need. But pretending you were on a desert island doing this yourself, you could say, we don't need to include 4 because it's blotted out already. We're only going to go to the next ones that are highlighted and then remove all their multiples. So the next one's 5. And now let's tell it to remove all the multiples of 5. There we go. We've removed all the multiples of 5. And they're a little harder to see where they land when you look at this pattern. But they do end in a 5 in our base, so they look kind of easy to find for us. If we could make this 30 wide, then they would look like neater columns again, because that would be divisible by 2, 3, and 5. Now, let's make it a little wider. We're actually going to go back to 10, because I think this is going to help us visualize the next thing I want to note. We're going to just a 10 by 10, where we have, and someone commented most of the primes they know. Let me try seeing which primes I know. Okay, 2, 3, someone comment if or when I get one wrong, if I do before I give up. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, I think 67, I think 71, I think 71, I think 73, I think 79, I think 83, maybe? I don't know. Okay, now I'm lost at that point. Did I get any wrong? So, here we can see that we're going to eliminate all the 2-digit primes, because that's really our question with this size of grid. We're like, we know 100's not prime. We know the primes probably in this small range. So we're kind of asking for a moment, what are the 2-digit numbers that are prime? Now, we've eliminated 2, 3, and 5. How much further would we need to eliminate on this size of grid? Well, we're only going to be eliminating multiples of primes. Everything else is taken care of. So we're only going to need to include primes, but even more than that, we're only going to need to include primes up to the square root of the largest number. That's because any number on this graph that is a secret composite that we want to eliminate has to have factors that aren't 1 in itself by being composite, and the factors have to come in pairs. And if we look at the lowest factor that's not 1 in any of the pairs, the smallest non-1 factor would be if the number is a square of a prime and the factors are that prime squared. It would be the square root of it. Otherwise, if the number is any other case but is composite, it'll have factors in some pair that come in, and each pair has something larger than the square root and something smaller than the square root. So we only need to check the primes up through 10, and then we know we've eliminated everything here, because any 2-digit number is either prime or has a factor that's smaller than 10, or up to 10. So we only need to eliminate 7, and then we know it all. What does that mean? That means, well, it's very easy for you to know the multiples of 2 and 5 in our base. Very easy to know that anything ending in that is not prime. Multiples of 3, people forget, but it's also easy. You add up the digits, and is that a multiple of 3? That's how I was skipping a lot of numbers on there. And knowing they weren't prime, like 51, added to 6. So I was only looking, when I was trying to remember the primes, at, once I hit past 10, what numbers end in 1, 3, 7, or 9. That eliminates multiples of 2 and 5. Their digits don't add to 3. And then I was trying to remember what the multiples of 7 were. But I was trying to go pretty quick, and I might have messed something up. I'm not sure. So if I had known the multiples of 7, we would have been set. And thinking about it, the only multiples of 7 that are going to be tricky in this range are 7 times another prime larger than 5. Because if 7's times one of these, we already eliminated it. So the only other ones we'd have to eliminate when I add 7 to my elimination here are going to be 7 times 7, 7 times 11, 7 times 13, and I think 7 times 17 would be too big to be in this range. Then we would think, what about the next prime? 11? No, 11 times 11 is too big. That's bigger than the square root of the largest number in our range. So to eliminate all the primes in this range, I'm going to tick on 7, but all it's going to delete is 7 times 7, 7 times 11, and 7 times 13. Let's see if that's right. Did it do that? It sort of shifted it. So we lost 91, we lost 77, and we lost 49. Yep. So here's the thing. 49 is really easy to remember that it's not a prime if you know your square numbers. 49 is a square number. 77 is really easy to know it's not a prime because of how multiples of 11 do that. The only hardest, trickiest prime, and I think someday I'll make an episode emphasizing this, about how I think the hardest, the sneakiest composite number, that the trickiest one to think would be a prime that's not, is 91. Because bigger than that, I don't think people would be that confident in their guesses of whether something's prime or not. 91's in the range where people might guess, I think that looks, and maybe I remember I saw that on a list of primes, because there's other ones that look kind of similar, but like 71 and stuff. But if we remember that 91 is 7 times 13, which I guess the multiple of 7 trick where you double the last digit, find the difference between that and the rest of the number, is okay at this size. We'll double the last digit and say that's 7 apart from 9. Uh-oh, it's a multiple of 7. If you can remember that 91's not a prime, then all you have to remember is that multi-digit prime, to know all your 2-digit primes, is to know that they're only going to end in 1, 3, 5, or 9. I mean, 1, 3, 7, or 9. Their digits can't add to 3. Or no, their digits can't add to a multiple of 3. And they can't be 7 squared, 7 times 11, which are really easy to see, or 7 times 13, which is a little sneakier. So, what if I wanted to go further? How many primes would I have to check to do 500 as my biggest number? Let's see, about how big if I go 16-ish by 16-ish. How many is that going to cover? That gets me 256. Let's go a little bigger. Let's do 20 by 20. We're up to 400. How many primes will I now have to remove to get all of the composite? I mean, how many fake primes, the composites that are lookalikes, that passed these 4 tests, would I have to remove? Well, any number that's not a prime here has some factors that can be broken down to primes that can't be broken down to 2s, 3s, 5s, or 7s. So, for example, the next one that needs to be removed would be 11 times itself. So, let's remove the 11s, and that blotted out all the 11s, with the smallest one being 11 times itself. Now, we would have to check 11 times any prime up to what passes 400. So you would have to check off a decent amount when you get to this stage. I will make a video sometime where I go through and calculate all the prime numbers up through 1,000. That will require us to remove all the primes up through the multiples of 31. So, but some of them we will have to multiply by bigger primes. Like we're going to have to look at like 7 times a really big prime also, you know. So we're going to, at some point, go through 1,000. Make sure you're tuned into the main combo class channel too, where this is always sort of like my more casual runs through things, sort of like hanging out with me for a lesson and hang out. Whereas there I have more concentrated lessons, and I'm sure at some point I'll do a version of something like this. And I had in my head one day a fun way to represent it would be to maybe get a giant stack of papers that are numbered and to have some methodical way of burning or destroying every second one and then every third or something like that, and seeing which ones remain. So we'll find a fun way to demonstrate this. But for now, we can note that to go up to 400, the square root of that's 20. So I'm going to need to eliminate multiples up through 19. And that's the amount the program runs there. If you eliminate all the multiples up through 19, there's your primes. They look a little sloppier in 20 than, say, 6 or 12. So let's go to like 12. That's a little neater for where the primes live. Same with, if I make it 6 and just like really long, that's also neater. So, all right. So that's fun. And like I said, at some point on the Combo Class channel, I'll do a more consolidated, thorough little 10-minute version of how to always remember every 2-digit prime. But whoever watches this stream can get a little practice in advance. So I kind of forgot that technique when I was really quickly trying to go through all the primes. Is what made me think of there's like a better way I could have actually remembered all the 2-digit primes without messing any up. So that's a fun thing to look at here. A lot of patterns we can observe. And I have this, when I bought a dictionary of numbers to replace my actual dictionary of numbers I left out in the rain, and the second one that was a different type I wanted to try out was just the numbers. No facts or definitions, just the numbers. Well, that was sorted sort of like tables of 8. It was really annoying in that it started off-centered. So they don't go from like a 0 to 7 or 1 to 8 as the last digit to start. It's like 2 is the first column sort of here, and then 1 is a little early and we'll consider it later something. But there's a way in that thing to line it up with 8. And so at some point we're going to, on an actual physical book I have, do something like this. But I'm still deciding how I'm going to like mark out primes one color, square numbers another color, something like that. Where the square numbers land would also have certain columns that were chosen or not in different widths. So that's that fun demonstration. What else we got? That's most of the ones that I currently downloaded. There's one more really cool one, but for a moment, I'm going to run inside. I need to just real quick use the bathroom and grab some water, but I also want to bring out a bunch of bird seed, and maybe having the bag of bird seed and refilling that a little bit will help us gain a squirrel or something. And while I'm gone, I'm going to return very quietly, just in case a squirrel or bird comes in the background. So leave a comment if I miss any squirrels or birds that I should look out for later if I'm adding timestamps to this and stuff. So I'll be back in a moment, and with my bird seed, leave some comments about what are the... Here, we'll remove this. Okay, yeah, this will actually be a good puzzle. So we have... Here's going to be the puzzle for while I'm gone, apart from, say, if any cool animals pass by. Here, in my base 10 width, or the one that's similar to that, I've removed 2s, 3s, 5s, and 7s. If I make the array really tall, what on here is highlighted but is still prime? I already gave a spoiler of one, that it's 121. What else would we have to remove if we wanted to remove the other sneaky ones? Use your brain, don't just look it up or anything. Also leave a comment if there's any cool wildlife. One last thing I forgot is, this is a cool thing that got sent to me to my private mailbox where you can send clocks and stuff. And when we turn it sideways, it will have all this stuff drift down in a strange, interesting way. So you can look at that as well. And I return with 3 items. Technically 4, but one was already brought, but I haven't shown it yet. We are going to take a little break from the math to look at comments and the current state of the nature around here while we do a little bit of the other thing I mentioned in the description, trying to lure more animals here. So, this is a good time to leave comments, by the way, running through what we had here. Someone said 143 factorial, they think. No, they probably meant 143. Careful with those exclamation points. It's always tricky. I want to put exclamation points in titles once in a while, but you can't put them right after numbers or it looks like factorial. Somebody said, is there a link to the notebook? Yes, if you look up Wolfram demonstrations and then Wolfram player, you can download the player for free. The really good version where you can like edit them and stuff is the paid one called Mathematica that I don't have. If any super fan ever wants to pay for me to use Mathematica, I would do it, but I'm not going to invest the money right now. So the free version is enough to run the Wolfram demonstrations, which there's a billion of. I'm going to, every couple streams we'll do a break to look at a few new ones I've got. So let's see. What is up, everybody? And somebody asked if I currently own a slide rule. I actually don't. Slide rule would be cool to have. If anyone has an extra slide rule, that mailbox link is in the description. So far, we've gotten quite a few interesting mathematical toys from there. A beehive and a stack of documents about primes and a small clock. Now, what did I bring? So I brought a bag of birdseed I'll show in a moment. I also brought something that the squirrels might like even more. I don't need the squirrels eating all my birdseed. That could be for the birds, hopefully, so I brought some walnuts. Unsalted walnuts are something that I know is good for a squirrel's diet. And so what I'm going to do is I'm going to sort of put a little trail of them. I'm going to put one way up on top here where they might be able to go. I don't even know if you can see all the way up there. And I'm going to put one a little lower on the clock. We're going to put one right there. We'll put one right here on that. Oh, yeah, because they're good climbers. They can get this stuff. We'll put one there, and we'll put one down there. No. The final one we're going to put on the desk, just in case, for some reason, the squirrel comes over to this corner of the desk and feels safe climbing over there. So, the walnuts, maybe the squirrel will like, but they also do like my birdseed, which I got a big bag of. And I left out the birdseed one time after filming, and they ripped a big hole in it. So, although I am going to refill the bird feeder, I need to do it over a bag so that I can, make it all work. I also have one other interesting item I've shown. Oh, man. I've shown before. Okay, it's all in the bag. Don't worry. Okay, how am I going to make this work? Okay. Okay, I need the bottom on and then screw the top. So the other thing I brought is, now some people are gonna, I realize it's a little weird because it might look like something to lure cats at the same time where I'm trying to lure birds. Trust me, I'm not trying to have any cats catch any birds. But I also have something over there that cats are able to eat. It's not gonna like attract them like catnip. Or like this other neat stuff called silver vine I need to show you folks sometime. This is just supposedly a type of grass-like thing that for when cats do that evolutionary quirk of wanting to eat grass, they eat a healthier version. Oh no. No, okay. Too much seed. Seed away from computer. Okay, seed issues. I didn't realize the squirrels ripped such a big hole in this bag. Okay, that worked. Now, here we got our bird feeder nice and full again. But I'm also going to put out the cat grass, because if the cats come, maybe I can encourage them to nibble on some grass that's not bad for their stomachs. So there's our bird feeder. And semi-ironically, it's not to lure cats to eat birds. I don't like when they do that. We're going to have the cat grass. The cat grass I will put, I guess for now, I'll let it sit in the planter, because there's nothing growing in that spot right now. And actually it's kind of heavy and this planter is pretty weak. I'll just put the cat grass in the corner because the cats like wandering around here. Now, we do have a massive potato plant like I showed. Look at that potato plant. It's crazy. You want a close-up of something wild? I didn't even plant that potato. I just put it in good soil and it rained on it. And wait, I need to unplug this for a second. And it rooted. So let me get a good view of this. This was a potato that's just like in the dirt. And all this stuff grew out of it. There's another smaller example. A potato that stuff just grew out of. So, and there's some garlic and or onion doing those weird sprouts. And some of these little sprouts are just random. They just came from the compost. The compost just had a little traveler in it or something. So, who knew if you just set down potatoes and you don't even plant them, they'll just start digging in and making roots and then making a thing, and I don't know, we'll see if it flowers or anything. It is poisonous, so if anyone ever tries this, do not eat it. Cool. Sam, yeah, I will email you back sometime. That's cool if you come by California. People who I have chatted with or who are super fans can always reach out if they're going to be in the Bay Area of California. You know, I could always, use a random hand around the combo classroom or something. And someone said, do not eat squirrels. Squirrels I will not eat unless I am in a very dark arc in grade -7, stranded in the woods in an overpopulated by squirrel zone. So, for no plans in the near future to eat any squirrels. The squirrels are pretty wild around here, and a lot of the neighbors don't like them. So I was house sitting for a neighbor who honestly doesn't even like my cats, because the cats just like chill all wherever they want, go try and stalk the birds for fun and stuff. And the neighbors are like more into the birds and not a fan of the cats as much. When I was house sitting there, the cats would wander around over to there and be like, oh my God, you're in the other yard. This is so weird. And the neighbors, I don't think, like the squirrels either. When I was house sitting, a squirrel runs over toward their bird stuff and knocks over a potted plant on the last day I'm house sitting. And I had to write them a note everything was good around here, except one of your potted plants shattered this morning, and I'm pretty sure it was a squirrel. Sorry, I guess. But they were totally cool with it. But all I know is I heard this big crashing noise, and I went out, and there's a squirrel just chilling 4 feet from there, wagging its tail. So squirrels can cause some chaos. They also often can eat too many of people's crops. So if you're growing a bunch of food, squirrels, kind of like deer, are like this too, where we get deer up in the hills, and they're really neat animals, and I love the times once in a while I see one. But they do eat people's crops up there, and people get annoyed at them and try and build fences that are deer-proof or even squirrel-proof. Oh, there he is. Okay, it went somewhere else, but it might have saw that nut. It might now know there's a nut up there. I hope I got that on the thing. It's hard to aim this. The squirrel was right up there. So, I think hopefully it'll come back and I'll capture it better. These squirrels are more brown. I know which type of gray squirrels you mean. There's also other squirrels, like in the field trip to the sundial in one of my episodes, the grade -1 finale. There's other squirrels we encountered when I go down to the marina that live in these little burrows and live in and around rocks and dirt burrows and stuff. And I don't know technically exactly what kind those are. I call them ground squirrels or something like that. And yeah, to Sam, who mentions wanting to help with number theory and being from SoCal. Definitely reach back out. Sometimes I'm slow on responding to people's emails, but I am definitely here. It's more my lack of liking to use technology that makes me not respond to people sometimes. Like, I don't like pulling up my email and doing all that. But I do like talking to people who like the combo journey and want to be part of it. So someone said a moose once landed on their father's car hood when he was in it. That sounds very dangerous. Hopefully he was okay. Moose are huge. Moose are one of those animals that some people, what's the right word? They underrate the strength of or underestimate. I think, let me look this up. It's kind of funny. I'm just going to look it up on my own here while I mention it, and I'll see if it's worth pulling up. But there's a lot of Americans, which is the place I'm from, and this is probably somewhat true in other zones of the world, but I think extra true for Americans because the place I'm from, the USA, some people can have a weird type of cockiness or overconfidence sometimes, and they polled a lot of Americans on which type of animals they think they could beat in a fight. And I want to see, like, a lot of them thought that they could beat insane amounts. Here it says, based on, this is just some sample size, so I don't know if this is 100% accurate of everything. This is just, one source's sample size. Let me show this for a moment. It's, this says that, based on this poll, what percent do you think you could beat in a fight? 72% thought they could beat a rat. That actually seems like a lot of people are too scared of rats. I feel like most of us could beat a rat in a fight. But then you start getting up here. Goose is more debatable if you could beat a goose in a fight if you had to. Those things are kind of intense when you come down to it. They're sort of assholes when you're at parks and stuff. They're not one of the nicer birds. Medium-sized dog is also debatable. So, and then you start getting up here, and it's like 12% of Americans think they could beat a wolf in a fight. It's like, maybe. 9% they think they could beat a crocodile. Now, maybe alligators and crocodiles are actually a bit different, but crocodiles are massive, and the strength of their jaws is insane. So, like, an elephant is just so big. What are you going to do to an elephant in a fight? 8% think they could beat an elephant in a fight. They just don't understand how big an elephant is. It would not even just feel a single thing you did to it. It would just step on you. And 6% think they could beat a grizzly bear. Now, what I've heard is in the hierarchy of bear dangerousness, a brown bear, you might have a chance. Oh, no, wait. The little black bears, which are sort of brownish, but called black bears, you might have a chance against. A grizzly bear, very unlikely. You've got to play dead or something. Scare it away somehow, but the fight, you won't win. A polar bear, you are completely done for. Polar bear is like another level. But still, some Americans are highly overrating their strength against gorillas, elephants, lions, and grizzly bears. So, I'm not sure what the cutoff is. It's a kind of funny conversational party question. How many of a given animal do you think you could beat in a fight? Of course, hopefully it won't come down to it. Like, how many squirrels would it take to over-dominate me? 20? I don't know. So, house cats are funny too. Like my house cats, they are pretty savage. I have to say, one of my cats, Sage, unfortunately does catch some birds. I'm trying to get him to stop, but he can get stuff. He catches rats too, and those actually can be helpful. There was a rat that was eating the stuff in our dishwasher and like messing up our appliances. And one of my cats, Sage, the small silky one, waited so vigilantly in the kitchen where he knows he's normally not allowed. He was like, I'm allowed this time. Waited staring at this spot under the stove where he knew it was hiding for days, literally. And after days, one day he had the rat and had gotten it. And so he is a vigilant and savage killer and can get stuff because he's small and sleek, but then can move really fast after being small and quiet, and has claws and craziness. But the cats have never scratched me. I pet them everywhere. I rub their belly. I scruff them by the back of the neck. I pick them up and move them. They have never scratched me. And they even like play with me with their paws, where they'll like not have the claws out because they're retractable, and they'll like pad me with their paws, and then they'll like stretch their claws, but not in me. And so they're really smart and really good at never using the weapon on me. But if it actually came down to it, I think it would only take like 4 of them to like completely decimate me, because they have some strength behind them. Someone asked, do I think drugs help sciences? Well, it's sort of controversial question. You know, as a teacher, normally in a math channel, the answer would probably be no, students never do a drug. However, I'm more of a real life channel. There have been times, I'm sure, in history where certain substances, whether it's a medication or some other thing, have helped people figure out something about science or math. I'm sure it wouldn't work as any great mathematician or scientist's daily ritual for very long to be using non-medication drugs. But, you know, there are stories I will reveal over the course of the grades that I know a decent amount about things like that. And I've been through a lot in the world, and I've seen many things as well. So we'll discuss drugs more in the future. But for now, my answer was, in the real world, you know, people use things, and there are medications, and there are things that are less medication-wise, and just be really careful and try and not make things habitual, and certain things completely avoid. There are certain drugs that certainly don't help sciences. So, and yeah, it depends. Do you consider daily coffee use as a medication or as a what? Or as, you know, it's a very spectrum-like blur. Now, there are mathematicians with histories of things like that. There was like Paul Erdős was a great mathematician who was prescribed something along the lines of what would be similar to, as far as I know, along the lines to what nowadays would be like Adderall or Ritalin or something, where a stimulant type of thing, often for ADHD people. And he used stuff like that really habitually, semi as a medication, maybe in other ways. It's sort of hard to get actual facts. And then his friends told him, you should stop your use of this, whatever stimulants he's on, for a month. And I bet you can't. And he's like, I'll prove to you, I could stop for a month. And then he completely stopped for a month. And then after the month, he was like, there, I proved it. I'm going to go back on them. And we've set back mathematics a couple decades by me doing that, because I didn't get much work done that month. But I proved that I could. It's probably healthy for him to take the month off. But there are interesting stories. And, you know, I have stories of my own that will come up in future grades. We get to be a little more open the more combo class is successful, and the more I know this is my job in the future, then I can be more and more honest about more and more things, you know. But in general, you know, I'm not advocating for use of drugs. Certainly, you must be very careful. Now, Paul Erdős is a very interesting mathematician. I love how he was very interested in open questions in math. And not only did he solve many himself and pose many questions, which sometimes posing the question is just as interesting as finding the answer, he also put bounties on them, sort of like precursors to the modern Millennium Prize problems, where now there are some problems where if you solve them with a thorough enough proof, you get $1 million. Before that, Paul Erdős would put out all these little bounties, like, here's the thing I'm interested in, I'll give $50 to whoever solves it. This one's worth $30. This one's worth $100. And made a lot of them get solved, so pretty cool. If I was ever rich, I would certainly do something like that. So, let's see. Thank you all for joining me and for all the cool comments. I'm going to close what I have open about how many people could beat what in a fight. We're not going to worry about beating things in fights. We are joining them today. And I'm going to keep looking back there because I feel like whenever I'm not looking or as soon as I leave, the squirrel's going to start eating all those walnuts. But I want to catch it. I want to be here when it eats all the walnuts. So we might have to have like a really silent moment. I might have to like hide in the clock or something. No, I don't think I fit in the clock. So, all right. Now, as you all join me here today, I showed all of the cool mathematical things that I had downloaded so far, but of course there's wide varieties of them that we will be able to look into in the future, because the Wolfram demonstrations page has tons of stuff. And the ones I basically got by searching some topics that I knew I'd already given you the intro to, like prime and base and stuff like that. And there will be many to come, because I can search other keywords and scroll through all of the different sections, look at ones about geometry and other things. But for now, we mostly will be switching our stream to just the camera view and enjoying some things about the combo classroom and answering whatever questions you have, which first of all, someone asked, have I done something cool on doing science? I'm not sure exactly what you mean by that, but I will say if you mean more scientific-based episodes where you see scientific reactions or facts as opposed to things about numbers, I do want to incorporate those a lot. And if you notice, if you watch the very intro to combo class, it wasn't really phrased like it was going to be so purely mathematical. That was sort of a rabbit hole I went down for a few reasons, one of which was I became extra addicted to it again, and it reignited a passion I'd had for numbers throughout my life on and off, and made me extra deep into, for some reason, I get a thrill out of studying math. And so I'm like, I better roll with that. You know, if I get almost like a drug-like feeling from learning math facts and studying math and taking notes about it, I'm like, I better keep rolling with that. That's productive. So that's one of the reasons. Another is that I can't show as many scientific reactions yet. Those take resources. I don't have a microscope. I don't have, a giant baking soda and vinegar stash or whatever. Oh, it's back. The squirrel. Did you see that? The squirrel knocked over that clock. Hey, what's up? I think the squirrel grabbed the walnut really quick, and in the process it knocked over... Okay, well, I was calling it a clock, but technically the clock part's missing. A thing that once was a clock. The clock part's probably somewhere. Now, as far as more scientific reactions, as I get more resources, I would love to. So that's the sort of thing that will require either collaborations, or if I have more money at some point, I'll buy cool science gear. Or people can, send me cool stuff like the awesome George Carosi has, which are various scientific-like demonstrations. One cool thing is this. You see this sand thing that's dripping? So it's gotten to the stage where most of the bubbles are trapping it. It's only leaking from minuscule portions, and so it's making this cool pyramidal shape. It looks like a cool desert landscape with pyramids. Now, let's see. So, about science, I would love to do more scientific reactions. We can do miniature ones, for example. Here is a lot of bubble soap, so I would run the bubble machine and maybe we'll do the bubble machine just pointing the other direction, but I don't want to do it when it's too windy because on my old computer it was like 3 or 4 years old, so I was okay getting bubbles popping on it. But this is, for those who have seen the Chronicles, I just got this new computer to replace the old broken one. And I want this thing to last multiple grades, so we'll try not to blast it with many bubbles. Maybe we'll have the bubble machine go a different direction for fun, though. And that's just a version of miniature science we could do. And what I call science when things are lit on fire. But there's other types I would love to do. And at the beginning of each grade, I always phrase it sort of like, we're learning a mix of math and science and language. And last grade, I got really carried away by the math, and I probably will again this grade. But I did phrase the intro to the grade like we're learning about math and other scientifical things. Well, not scientifical. Yeah, luckily I didn't say scientifical in the episode, but yeah. So we'll do that more. Now, one thing I would love to work with someday is, so I'm in the Bay Area of California, and here there's this thing called the Lawrence Laboratories. Is up by a park that I hike in a lot, not far from the park I like to hike at, like a forest-like area, is both the big Lawrence Laboratories part of it, and there is other ones. There's one called Lawrence Livermore. I'm thinking of the one called Lawrence Laboratory in Berkeley. And there's also this thing called Lawrence Hall of Science. I used to go sometimes as a kid, which has really cool versions of what some would call stuff for kids, like a Toro Flux or like a weird bubble machine, but that I think is really cool science. And I think those are things that we were right when we thought those were cool as a kid. Maybe we were wrong when we were like 15 or 20 and decided bubbles aren't that cool. And maybe we were right when we were like 8 and thought they were. So we're going to, someday maybe, I would love to work with either the Lawrence Hall of Science, if I could like film in part of there with their like way bigger versions of science toy like things, or somehow work with the Lawrence Laboratories, where they have literally discovered some of the elements that are on the periodic table. There's that Lawrence Laboratory in Berkeley place has multiple elements named after it. I think Einsteinium was discovered there, or like first created by a human, because they're not very naturally common. They have one called Berkeleyum. There's one called Lawrencium after the Lawrence Lab. There's multiple named after it. And so that would be a dream, is to be able to film in one of those places after hours. We'll see which grade we manage to pull that off. Now, sometimes we will find math in the nature, and other times we'll just be taking a break to appreciate other things. I was thinking about how the combo and combo class not only just means combo of a lot of topics, but if I had to simplify a sort of dichotomy of the combo to oversimplify it, to a degree it's the combo of the logical things I want to present to the world and the almost spiritual other side of nature and other parts of our existence that are hard to quantify and know which numbers describe. So, well, that's, we got a combo going on. Of course, sometimes we'll even find direct numbers in the nature. And for example, like I mentioned earlier in this stream, here's a banana that I have because I have a whole batch of bananas in the episode I'm filming this week for the main combo class channel that'll be out maybe on Sunday or so. It is a snack break, which every 5th or 6th episode, I do something like a snack or science break there, where we depart from a more direct lesson to sort of enjoy the scenery and learn about plants and stuff. However, this time, it's the most mathematical snack break yet, because we're actually going to have a geometric connection between bananas, beehives. Okay, last time I touched the beehive, a spider, I think, came out of it. You guys got to see the beehive earlier, or wasp nest earlier. But wasp nests, bananas, and other things about math. So that's a connection that I've never seen noted. I couldn't find it on Google when I tried to look up the connection. I mean, it's a connection that is more obvious with the wasp nests and beehives maybe, but that is in bananas. So we're going to have a sort of scientific snack break for this week. And I actually brought out another type of banana that I got because when I was shopping for them, the produce place I went to had so many types. They had these giant plantain ones that I almost got because they were so weird for a banana type fruit, but they looked so un-banana-like. I didn't think viewers would even believe it was a banana. Okay, the squirrel's coming back. There's two of them. One jumped. I see the other. Okay. One jumped and one's kind of out of frame, but when there's two, that's fun because they play and they do crazy stuff. So the two might chase each other over here. Now, I did bring one of the types of banana I did get, which is one I got for its like rectangularness. Now, this isn't the geometric thing I'm talking about, how many sides are on the outside of a banana, but this one, funny enough, almost looks like it wants to be a rectangular prism, but this side bulged into two instead, and so it's like a pentagonal almost shape. That's not the geometric thing. The geometric thing is sort of like, despite the pentagonal shape, they have a connection with the beehives, but I thought this was interesting. It's a slightly different banana. It tasted sort of plantain-like when I had another of the type. Also, bananas are just inherently funny. You can slip on them like a banana peel. They look like a particular thing I'm not going to mention. And they're just funny. Like, you know, you see monkeys eating them in the woods. They're strange colored, long fruit. So, inherently funny. But we're going to look at some math within them as well. So, someone also mentioned surface tension, which is pretty neat. We could look at things like that at some point. And if people want to suggest things that are topics, they can always leave a suggestion in a comment for an easy-to-do science reaction. Whenever someone leaves a comment about a recommendation for a math thing, it would get put way at the end of a long list of topics I already have planned. And often people name something simple enough that it's already part of one of the topics I'm planning. But I don't have as much planned for the science reactions we're going to do around here. So if anyone has some like insane version of baking soda and vinegar or whatever they want to suggest, feel free to leave a comment. So, okay, so it grabbed the nut that was up there. I'm going to put another nut up. Okay, I bet you it's going to get that nut in a minute. Okay, we're back to the quiet fake ASMR math science part where we talk really quietly in case the squirrels return and decide to play. So, I feel like they might grab that. We'll see. Alright, we'll just have to wait. Squirrels are doing all sorts of new fun stuff this season with all the bird seed spilled and such. They just come around here more often and like hanging out and being wacky. They're knocking over clocks, they're running 2 in a row, and so on. So, someone asked what school I went to for education. It's a really common question I've been asked that I've sort of gone over in earlier streams, so I think before long I'm just going to make a bonus video that answers that to point people to, because I have, to a degree, gone over that enough times recently. One thing I did want to note I was thinking about is I have all these puzzle cubes here and my cubic banana, and a bunch of cubic dice. But the puzzle cubes, a lot of them like a 3x3 like structure. Turns out puzzles are really good at designing for a 3x3 thing. This thing called the Soma cube, as a nickname often, is supposed to fit into a 3x3 shape. This is a 3x3 shape. The common Rubik's cube is in a way a 3x3. Now, it is a 3x3 if you count the center, but the center doesn't even have a color on it. So if you count how many cube-like units actually have a color on it, well, it's actually one less than 27, which would be 3 cubed, because there's that center. Then you could get into how many of the parts actually are doing anything, because the centers, you kind of can't move the centers. If you try and move the center one, it's like you moved the other two sides. The centers are basically saying, I'm the red side. If I move it, it's just, okay, the red side. If you look at the math, which I'll explain more in some videos, the centers are sort of fixed in a way, and we're sort of just doing turns that are right, left, up, down, or reverse versions, or front, back, reverse versions and stuff. Now, the 2x2 cube is also sort of encoded in the 3x3 cube, but apart from the fact that we could use this as a 2x2, I think the 2x2 is a better puzzle, because the 3x3 would take you like more than a year probably to try and figure out yourself. Everyone who does it, almost everybody, did it by looking up an algorithm of some sort. Maybe they edit the algorithm themselves, but to solve this without knowing anything about a Rubik's Cube and not looking anything up, it's way more unlikely than people act. People might say they did that, but highly unlikely unless they spent a couple years working on it. Or 8 hours a day for a month or something. So, really, you gotta sort of learn algorithms to crack this fella. You can solve smaller puzzles, like here I solved what's called the first layer, where we have all of those, and we have lining up with the centers there. Once you get past there, it gets trickier to fill in the others without messing up the first layer. And the first layer can be any color, just happens to be orange there. This puzzle, the 2x2, you could figure it out yourself if you were stuck. So this one is almost a better puzzle in terms of, might be even more likely to make your brain think as opposed to giving up and looking up an algorithm. So those are underrated. All right. I haven't researched Bram Cohen, who someone mentioned. I have seen some cool things about 3D-ish Rubik's Cube-like things, which are interesting. And you can take cubes into other dimensions. So maybe I'll look into that stuff at some point. Now, someone says they got the checkerboard cube puzzle, and when not solved looks like a snake. Yeah, I actually got 2 of these. I believe these were from our fella George Carosi, who sent some cool stuff. Look at these neat mountains that are forming. Now, since it's going so slow, I will tilt it a little bit to give it a little more wiggle room. And now we'll see what happens there. It is going to collapse our mountains a little bit, but we got to see them. And then you have this puzzle cube that can form into a cube, or there's a state where it turns into a rhombic dodecahedron, which is pretty cool. Let me see if I can get that. So, where's my rhombic dodecahedron? Almost. And this one's bigger than the cube. The rhombic dodecahedron, when you make it, is hollow and ends up bigger than the cube. So here's the rhombic dodecahedron. Pretty cool. But then, which is hollow. Then to make it into a cube is really hard. I keep getting stuck trying to make it into a cube. In any case, this one doesn't even have a 3x3 structure. It just has its own wacky stuff going on. But I was thinking about a lot of puzzles, and I'm sure there's more out there, like a 3x3x3 thing. It even holds true for 3x3s in 2D, where magic squares, for example, and ways of expressing intransitivity I will show with weird dice puzzles. A lot of those things start getting interesting at 3x3 and upward, or in this case 3x3x3. So yeah, I'm gonna stop messing with this thing, or I don't know. Oh, whoa, I got it. Okay, cube. See how it's way smaller than the rhombic dodecahedron was because that one was hollow? There we go. I'll unsolve it later when I want to mess around with it. Now, I guess for fun, we will test out a few bubbles, but I'm going to point them a different way from the computer screen. Now, this is going to get to a casual portion of the stream, which some may like more, some may like less. If anyone leaves because we're just doing bubbles and chatting, make sure you've checked out the latest episode on the main combo class channel. And I will have on this channel coming soon, maybe even later today, some shorts on each channel, on this channel and on the combo class channel, which will be the first ones on there. I want to get the shorts tab people knowing about that channel too. And there will be a slender salamander bonus video. And then this weekend we will have some surprising banana math. Oh no, this cube broke. Next week we will get back to straight numbers. I just thought it was a good time to work in the snack break episode because it was genuinely something I thought of this week about bananas that made me just go, maybe I'll do that as this week's episode. So we shall see what that's about this weekend. And people are mentioning there are many 5 symmetries in fruits: apples, oranges, and bananas. Now, although you're noting 5 symmetries, there are other symmetries going on in bananas as well. So we'll be looking at some ways of looking at symmetries in bananas for sure. But from there, I'll leave the rest for this weekend's episode that, can be its own little self-contained snack, mathematical version of a snack break. Someone said you can't see what I'm doing with the circle, and I'm not sure if you mean this. I can move all this stuff, and what I was we kind of buried the pyramid in the middle of there. I guess I might as well turn it whenever it's the other way to give ourselves a little extra background show if the camera ever points that way. But we were going to just try a few bubbles. Now here we're going to try a challenge. Can I fill the bubble machine wearing these? Are these going to be more helpful or less helpful? Now what I'm seeing right now is down. These are pointing downward. Right now I can see the camera. You can probably see my eyes and some weird reflection maybe. So here I'm looking down. Now is this going to be more helpful or less? Okay, no, I'm going to do it after I get away from the computer. I don't want to spill stuff on the computer because I'm wearing these glasses. But, okay. Now, it's really hard to do things like this. It's sort of like you're in a video game. I'm not sure if you can even see me. Yeah, where is this? When I'm looking through the glasses, it's sort of like a weird video game. And it makes it feel like you're in like third person or something. Okay. No, okay, I'm going to mess up everything if I have these glasses on. I cannot have the glasses and the bubbles and try and keep the computer safe. So, this is a new bubble machine. My old one got rained on a bunch and only lasted 1 grade, but bubble machines are getting cheaper these days. They're good at making bubble tech now. So, this one isn't hyper powered, and it really depends how it acts on how the wind is going. There's already a little bubble fluid in there, assuming that's not water, but I'm going to add some. Now, let's see. Okay, they're going right toward the computer. Yeah. Okay, we're going to get the smallest amount of bubbles. We're going to face this way so that the wind is on our side. Uh-oh, I unplugged something. Okay. Now, there is going to be, at some point in grade -2 or 3, another bubble episode. I know we already did a bubble science episode. But there's more to say about bubble science, as well as bubble math. And there's some traits about threvenness, about how bubbles meet if they connect, that is quite interesting, and we will definitely have to look at. There was progress on what's known as the double bubble conjecture just last year. And the further analogs like the triple bubble and quadruple bubble conjecture. All right, well, those are nice. We'll return to our science of those later. Another sequel science episode we might do is I did one called Apple Science last summer. And we're going to have 1 billion apples in that front yard that I share with neighbors, but none of us can add up to eating enough apples. I have to make applesauce and all this crazy stuff. we're going to need to figure out even crazier stuff to do with the apples. So leave comments if any of you know any cool experiments involving apples that I haven't tried yet. So, my favorite though is this. Do they sell giant versions of this? Let me just look this up real quick. Do they sell a massive Toro Flux? I need somebody to make me a massive one of these. So, I'm not seeing them in different sizes, I don't think. Okay. I need an engineer out there to make me a huge one of these. Because then we can have it be in the folded state. And then when we need to draw attention to a cool statement or whatever, spring it into life. Now, that's most of today's stream. Leave any last questions or thoughts you have, because I'll probably be logging off pretty soon. But like I said, there will be a lot of bonus content coming this week. And somebody mentioned that Mathologer has a video about Toraflux math. And yes, not only did I watch that a while ago, because I have seen all of the Mathologer videos. That is one of my favorite, if not my favorite, math channels. Also, since I support Mathologer's Patreon, you see my name at the end of the new episodes. And, because he puts all those, and if you do the same for me for certain tiers, you get your name in my whiteboards. And I'm going to start putting them in the descriptions of things like the streams as well. Because I've been putting my Patreon's names in the main channel descriptions for any tier. Currently, later I might not have room, but now I got room for all of them. I'm going to put that on this channel too, once I copy them over. Because this channel's growing so quick. Now, hope everyone has a really nice day, or wherever they are. To those who say they missed it, rewatching the streams is always good. I will make sure to, as usual, have it save as a watchable video. And if I have time, I will try and add some timestamps at some point. But I don't always have time for that. Often I want to use all of my energy for that little period of the day on the stream to make the stream maximally good, and then I don't save myself energy where I want to re-watch the stream looking for timestamps. So if anybody ever watches it after the fact and you're already watching the version that shows minute times for stuff instead of showing how long it's been, then you can leave some timestamps in a comment of any particular moments that you liked or any particular topics, and that's super helpful. I will pin whichever comment is, the most detailed timestamps or whatever. So if you ever have time, that helps, but I'll see if I have time to add some of my own for any particular moments later. This one luckily was a pretty visual stream, so I think people skipping through will get to see, oh, there's when we were doing primes, there's when we were doing that. But hopefully some people like to watch the whole thing too. So, love you all so much. Make sure that if you want to chat with me anymore, you're on the Discord, possibly the Patreon. If you, have any type of money in your life, the Patreon's very helpful. And the subreddit is another place, which I actually haven't checked the subreddit in a minute, but I'm going to go there and see, add a post or two myself, because I actually use Reddit more than Discord normally. Apart from, I check the combo class Discord when I can. And those are some cool links. Make sure you're on the other main combo class channel too as well. And one cool last thing to note is that I've randomly had a bunch of videos that related to 7 recently. Kind of ironically, I made a video about 7's bad at dividing. 7 was then a good example in my modular division episode. 1 divided by 7 in a certain mod. And we had other 7-y stuff going on. There was another video where somebody noted I used a lot of examples starting in 70 something. So it's been a 7-y week, which is all right, we can get used to on the big scale of things. 7's pretty nice. And although my video was kind of roasting 7, that is the most viewed non-short video on this channel now. So to anyone who came here from my 7 video, that's awesome. Those viewers, I think, who come from a longer video are more likely to be a consistent, cool viewer over time than the ones who come from the shorts, to be honest. Even though a lot of viewers who came from the shorts ended up becoming cool combo lords for the ride. But that's just a little extra rant. I love you all so much. Catch you